Electricity Fundamentals, Engineering Masterclass, prepared by Engineer Adil Saleh. Overview. Entering the world of electrical engineering forces you into a massive, chaotic landscape of equations, components, and overlapping theories. It is incredibly easy to get lost in the noise. We are going to tear down that wall of isolated concepts. We will organize them into a single, elegant framework. This diagram shows the architecture of electrical systems. It divides the entire discipline into three distinct pillars. Pillar 1 is core dynamics. This represents the microscopic physical laws and theories, like Ohm's law and impedance, that dictate how an electron behaves. Pillar 2 is grid infrastructure. This covers the macro-scale hardware, the transformers, cables, and capacitor banks, required to generate power and move it to a load. Pillar 3 is shielding and control. These are the active safety mechanisms, such as earthing systems and circuit breakers, that prevent the kinetic energy of the grid from destroying the physical hardware. Engineering clarity comes from observing how these three pillars interact continuously to orchestrate the modern power grid. This diagram illustrates the electromagnetism bridge. This is the microscopic bedrock that makes all subsequent macro infrastructure possible. We begin with the magnetic field, labeled B. This is an invisible force multiplier. By manipulating this invisible force, we induce a highly specific physical reaction. We force the directional flow of electrons through a conductor, which we define as current, labeled I. When we scale this microscopic reality up to an industrial level, the mechanics remain identical. A mechanical turbine at a power plant is a massive device built for one purpose: to force these exact magnetic interactions at high velocities. By harnessing this precise electromagnetic relationship, engineers are able to generate enough force to push physical power across an entire continent. This graphic maps the macro journey of the electron. It traces the path from generation of the power plant through long-distance transmission down to local distribution. The massive vulnerability in the system lies in the center. Transmitting power over hundreds of kilometers of physical wire exposes the energy to significant physical resistance. This diagram shows the absolute mathematical dictator of grid design, the formula for power loss. The equation dictates that power loss equals current squared multiplied by resistance. If we transmit power at a low voltage, we must use a high current to deliver the same total energy. Because current is squared in the loss equation, this mathematically squares the heat loss, melting the infrastructure. To solve this, we insert transformers into the grid. These devices physically manipulate the variables of Ohm's law. By stepping up the voltage to extremely high levels, the transformer forces the current to drop proportionally. Because the lowered current is what gets squared in the equation, the resulting thermal loss is reduced to near zero. This matrix characterizes the different types of electrical flow. To execute that extreme voltage stepping efficiently, the grid requires alternating current. Alternating current, or AC, uses an oscillating flow. It is the standard for long-distance grid infrastructure, specifically because its voltage can be easily stepped up and stepped down by transformers. Direct current, or DC, is a unidirectional flow. It cannot be transformed as easily, making it essential primarily for battery storage, electronics, and specialized point-to-point transmission. We also utilize three-phase power, which layers multiple AC cycles. This provides a smoother energy delivery that is highly efficient for massive industrial motor loads. Grid infrastructure exists as a sprawling, physical manifestation of mathematical compromises designed to defeat thermal loss. The grid is a massive kinetic engine, constantly on the verge of destroying itself. To operate safely, it must be contained. We must actively shield the system against three primary threats: thermal overloads, environmental strikes, and unintended ground paths. Unchecked thermal limits cause massive heat buildup, leading to fire risks and catastrophic infrastructure melting. Massive atmospheric voltage spikes, like lightning, inject sudden, lethal energy into the grid from the outside environment. Leakage currents can find unintended paths to ground, posing lethal electrocution risks if that path involves living tissue. This table outlines the Defender's toolkit. These are the specific engineering hardware components designed to automatically mitigate those exact threats. Circuit breakers use overcurrent as their trigger. Their automated action is to physically interrupt the flow of electricity to protect infrastructure from melting. Earth leakage circuit breakers, or ELCBs, monitor for minute current imbalances indicating a leak. They trip instantly at highly sensitive thresholds to prioritize safety and protect life. Surge arresters trigger during transient voltage spikes. They divert the excess voltage safely into an earthing system without stopping the normal power flow to the rest of the grid. These safety systems act as highly sensitive mathematical tripwires. They are designed to break the circuit the exact millisecond the physical forces fall out of balance. This brings all three pillars together to analyze a high-stakes event, a physical grid fault. In Phase 1, a tree breaks a high-voltage line, causing resistance, R, to drop to near zero. In Phase 2, the microscopic physics react instantly to the macro damage. Directly following Ohm's law, the sudden drop in resistance causes the current to violently spike into a massive harmonic overload. In Phase 3, the shielding pillar detects the mathematical irregularity. Protective relays read the abnormal impedance and fire a digital trip signal. In Phase 4, the solid-state circuit breaker receives the signal and trips in milliseconds, isolating the fault. The system survives. Mastery in electrical engineering requires understanding this exact unified sequence of physical cause, mathematical reaction, and automated protection orchestrating the modern world.